In section 11.6, there's two objectives you're going to cover. It's objectives 8 and 9. You're going to learn how to compute confidence intervals for 90, 95, and 99% confidence levels, and then determine the margin of error within an interval. Let's go ahead and take a look at the notes. First thing we need to discuss is what is a confidence interval. It's actually something that's used quite a bit when you listen to the news. And they might say something, for example, during a presidential election, that they are 95% confident that 64% of the population will vote for a particular candidate. And that's what we're going to figure out today, is how those are computed. So by definition, a confidence interval is an interval where we think the mean will fall given a certain level of confidence. And a confidence interval is structured with a standard normal curve. If you look at it here, you're going to see if we go one z-score on a standard normal curve, it's 98 or 68% of the data. So if you went one z-score to the right or to the left, you would be 68% confident that all the data is there. If you go out to two z-scores, that's about 95% confident, roughly. 3 z-scores is about 99.7% confident. And we're going to end up using some different precise percentage levels for confidence intervals. And we'll talk about those in a bit. Here's the formula you actually use. What you do is you take the mean of your data set and you add or subtract what's just called the margin of error. This is the margin of error. And all a confidence interval says is that our mean has some error to it. When we do statistics, we sample data to make inferences about the entire population. It's too expensive to survey the whole population, so that's what this says, is look at the data, the mean from your sample, and we're going to say how much error would be in there to make assumptions about everyone in the U.S. Some things to keep in mind about normal curves. It's completely described by its mean and standard deviation, and that's why we can use it. The z-score is the number of standard deviations the data is from the mean, and that's where on here the numbers 1, 2, and 3 are the z-scores. The second point, the mean is located at the center of the curve, and therefore we have a standard normal type of distribution. It's equally symmetric. The third thing is standard deviation determines the shape of the curve. So depending how many deviations we want to go from the mean. And let me show you some more information about these. Now this slide here is just going to show you how the z-scores relate again to the standard normal curve, which is what we've been doing for the last two sections. Look at the z-score calc here, and you're going to see it says x bar minus mu of x bar minus sigma of x bar. Well, you're used to seeing this as a z-score. For this chapter, we've done take your piece of data minus mu, which is the population mean, divided by sigma, which is the population standard deviation. Now, these little x bars here are just saying section 6 is different from section 3 in that we're not just looking at one sample. We are taking many, many different samples, and from all those samples, we're taking averages. And that's going to hopefully give us a good picture of what the population would really look like. Again, we're not going to sample the whole population. It's too big. Don't be thrown off by that x bar. It's just fine if you can equate this as the z-score. You'll be just fine. Let's revisit again. The z-score means how many standard deviations a piece of data is from the mean. And here are 4 nice scenarios. I would put these again on your study sheet for the final. This first one here says, what if we go a z-score of 1? If I do one z-score, it'd be 1 to the right and negative 1 to the left. If I found the area under this curve like we did in sections 2 and 3, 68% of the data sits there. So if we use a z-score of 1, we're going to be 68% of the data will be captured, so we're 68% confident we have the right answer. And again, this is about 1 standard deviation, because that's what the z-score means, is how many standard deviations I am from the mean. The next one they typically go to is down here in the bottom. If we do a z-score of 1.645, which is going to roughly be about right here. The area under the curve here, if you find it, is going to be 90% of the data sits there. So if we use a z-score of 1.645, we've done 1.645 standard deviations to the right and to the left of the mean. And again, 90% of the data is here. The next common one in statistics is here in the upper right. If we do a z-score of about 1.96, which is roughly 2, and you find the area under this curve, 95% of the data will sit there. And this is a standard deviation, is about 1.96 standard deviations. And the last one, if we go 2.576 standard deviations, which is about right here, and look at the area under that, that will capture 99% of our data. And they typically say this is 2.58 standard deviations. So what we're going to use is the confidence interval formula from the first slide. And someone has to tell me, how confident do I want to be? Is it this one, this, or this? So that would be given information. On your formula sheet for the final, write down these 4 pieces of data. Put a 95% confident, for example, has a z-score of 1.96, and so forth. Now again, I mentioned this earlier, this could be a little confusing, but here's the difference in section 6 versus 2. Section 2 and 3, we use the regular mean. This is the mean of all the samples. If I wanted to know how the entire U.S. did, for example, on the ACT exam, and I didn't want to have to calculate everyone's score, I might take a sample from Montana, a sample from New Jersey, a sample from Minnesota. I would take all those samples and compute their mean. Okay, so this notation here, mu of x bar, is just the mean of the population of all of my samples. Okay, it's all the samples together. Versus what we've done before is you're used to looking at just mu. Now for our purposes for this section, if they ask for mu of x bar, it's just mu. It's just the mean, same thing. Now the standard deviation, you have to be a little careful. You're going to have 2 different scenarios for this. They're either going to give you the standard deviation of the population. They're either going to say sigma is a certain value, and you're just going to use that, or they're going to say they want the standard deviation of all the samples. So sigma is a standard deviation of the population, okay? Just as mu here was just for the population. Sigma x bar is the standard deviation for all the samples. And if they're using all the samples, all you would do is you're going to take the sigma value, which is what they're going to give you, and you're going to divide by the square root of the number of samples. This will make more sense once we do a number example. So what does a confidence interval really mean? What you're going to end up doing is this. You're going to take the mean, and you're going to add or subtract from it the z-score that we're choosing to use, either 95% confident or 90% confident, and then you're going to times it by either the sigma over the square root of n, which is the standard deviation of all the samples, or sometimes they're just going to give you the general standard deviation. So you'll just have to read the problem carefully to see, do you actually plug in all of sigma divided by the square root of n, or sometimes it'll just be the sigma you put in. Okay. By definition, here's what this says. By using a sample, we can make inferences about an entire population, but only with a certain level of confidence. We're only going to be 95% confident or 90% confident or something of that nature. When reporting statistical findings, your confidence level should be at least 90%, but typically 95 and 99 are most commonly used. Let me show you an example here. All right, here we go. A candy company produces 60,000 bags of candy each year. From the data on its production, the company has learned that the weight of the bags are normally distributed with a mean, or mu, of 7.5 ounces and a standard deviation, which is the sigma, of 0.04 ounces. Part A, between what weights symmetric to the mean do 95% of the bags fall? Folks, all you need to do for this section is this. Take your mean, add or subtract, whatever the z-score we want to use, and then we're going to use, in this case, the sigma, because we're just talking about this particular population. Okay, this is part A. So the mean for this case is 7.5, plus or minus. They want us to be 95% confident. So go back to that data I gave you, and you're going to have to look this up and realize that's a z-score of 1.96. So I put that in for my z-score, 1.96. Now in this case, it's just the standard population, so I just put the regular sigma value. To simplify this, what you're going to do is you're going to take 7.5 plus this value, and then 7.5 minus this value. What you're going to find is that the mean is going to fall in between the numbers 7.42 ounces and 7.58 ounces. So what we can say is we are 95% confident that if I randomly select a bag of candy at this company, that the average weight is going to be between 7.42 and 7.58 ounces in the candy. Okay, let me show you the difference with Part B. Part B is going to use the other formula. It says each day 25 bags or packages are randomly selected for quality control of weight, taste, and appearance. The mean weight of these packages is recorded over time. 95% of the mean weights will fall between what limits? In this case, they are doing random samples of 25 packages. So that's how large the sample is. The key here is they're doing these, it says over time. So they're going to be doing it a sample, another sample, the next day's sample. So here I want to take the mean of all the samples and do plus or minus the z-score. And because it's of not just one sample but many samples, I would use this formula. The only real difference in this is that this guy here is using the square root of n. Other than that, it's the same thing. I'm going to use the original mean from before, which is 7.5 ounces. Add or subtract. My z-score, I want to be 95% confident. Back at that picture, it shows it's a 1.96 z-score for that. And then I'm going to take the sigma that we had before, which is 0.04. And this time, because I've done many samples, I'm going to divide by the sample size, which is the square root of 25 in this case. When you readjust the numbers, you're going to find now that the mean of all the samples, the new mean, is going to fall in between 7.48 ounces and 7.515 ounces. So this is, we are 95% confident that of all the samples we take every single day, the weight distribution is going to be between these two values. There's not a big numerical difference, but it is a different calculation. And this is really what you want to take away from this section, is this example right here. Now, there's about 3 more examples I'm going to do. They're somewhat similar in nature, but I encourage you to listen to at least one more and then decide if you want some more examples. Here's another one. Suppose that in a test of 200 light bulbs, it was found that the distribution of the lifetimes of the bulbs was approximately normal, which means we could do normal distribution. The mean was 2,461 hours. The standard deviation was this. So I'm just going to jot down the mean. And then the standard deviation was this. By the way, the sample, if they were doing one, we haven't really done many different samples. This is just one sample they're doing. So they're not doing multiple samples. They just did one test of these light bulbs. So we're just going to end up using, for this case, the normal confidence interval. So Part A says this. Symmetric to the mean, between what approximate lengths of life did 99% of the bulbs fall? So for Part A, we're just looking at this one particular sample, so I'm going to do just the normal mean plus or minus the standard, the z-score, and of sigma. The mean of this, the average length was 2461 plus or minus. They want us to be 99% confident. 99% confident, the z-score that's associated with that is 2.58. And then the standard deviation is 298. If you simplify this, you're going to end up getting this number plus or minus 768.84. So you're going to find that the mean of this data is going to fall between So the lifetime hours, we are 99% confident that the life of this light bulb is going to range anywhere between 1,692 hours and 3,229 hours. Okay. Now, let's notice the difference in Part B. If other people did the same test, so we're going to have other people, different samples, with 200 similar light bulbs, between what approximate length of life should you expect the mean to fall 99% of the time? The difference here is this is going to be other people. It's going to be many samples are happening. So when there's many samples, I just adjust the formula. The formula now is the mean of all the samples, plus or minus my z-score. Only difference is here. Take the standard deviation and divide by how big the sample size is. Again, this was one sample. This is going to be many samples. That's the only adjustment. The mean is always going to be the same calculation or the same number, so I'm going to use 2461 plus or minus. I want 99% confidence, which is a 2.58 z-score. Standard deviation is 298, and I always divide by the square root of how big my sample is, which is 200. If you crunch this out, what you're going to get is the average mean of all the samples is going to fall between 2407 and 2515. So the average length of a light bulb of all these samples, you're going to notice is quite a difference in terms of the results. Now in this one, I just want us to read it and determine which confidence interval formula are we using. Do we take sigma divided by the square root of n, or do we just use sigma? Let's read it and make that determination, and I'll just plug the numbers in for you. A superintendent of a large school district is worried that juniors will not do well on the required state test in reading. Past years of students provided widely varying means for the district, but the standard deviation has been close to 9.2 points. The superintendent uses a release form of the exam to test 72 randomly selected students in different high schools 2 months before the state test. The students score on average 135. Estimate the mean of all the juniors in the district. So what we want to think about here is, are we looking at all of the samples or just a given sample? The key to this problem is right here, is he randomly tests 72 students in different high schools. So he is actually doing many samples here, okay? This is many samples. He's going to different high schools. If he had said he just went to one high school and did it, that would be a different formula. So we're going to use the mean of all the samples plus or minus the z-score, and then we're going to do sigma over the square root of n. Now, the one thing I'd have to ask him is how confident does he want to be? He needs to tell me that. Let's assume he wants to be 95% confident. Okay, so now we can fill this in. All you need to do is put the mean of the score, which is 135, plus or minus the z-score with 95% confidence is 1.96. Standard deviation divided by the square root of our sample size in this case is going to be 72. This is going to give us 135 plus or minus about 2.13. And when you do that, we're going to see the mean of all the samples is going to range, fix that, between 137.13 and 132.87. So he can be 95% confident that if he randomly selected a student in his school, that the score of that student would be somewhere within this range. Okay. Another example, if you just want to determine which formula am I using at the confidence interval, let's just read it and determine, or skip on to the last slide. In 2004, the mean score of high school seniors on the SAT verbal test was 504. So I'm going to jot that down. The standard deviation was 111. Suppose 40 randomly selected seniors, that's my sample size, is 40, in a particular district were asked to take a similar test and their mean score was 527. So that is actually the mean of a particular sample. So X bar here is 527. Okay. He wants us to give a 95% interval in which the mean score of all the seniors in the district is likely to fall. Now, this one has a little twist to it. They're just doing one sample. They're not doing many samples. But they are trying to make an inference for a population given a particular sample. In this case, folks, this is a little trickier one, we are using this standard formula here. We're going to take a particular sample and add and subtract from it, z, and we're going to do sigma over the square root of n on that one. And this is, again, because we are taking a particular sample and we're looking at this sample to make inferences about the population. I wouldn't worry as much about this particular formula, but if you were to do it, it's going to be the 527 plus or minus 1.96. Our sigma is 111 over the square root of 40. And I'm just going to leave it at that. If you understood the slides before this one, those are the ones that you're going to be encountering more. This one is just a little more higher level statistics, and don't worry about it as much. Okay, this last slide is important. You are going to be tested on it in your final. Choices that affect the confidence interval. This right here is our standard formula for the confidence interval. Again, we know sometimes we don't divide by the square root of n. Remember, it's very important. The margin of error is this component right here. What you do is you add and subtract from the mean how much error there is. So there's a margin of error. So you want to be able to understand this. There's two things that affect the margin of error. As there is an increase in the sample size, if this sample size right here increases, what's going to happen is the margin of error will decrease. And think about it. An increase in the sample size means you're more confident, you're asking more people, you're going to get a better variety of answers. Hopefully your margin of error is going to be less. You're going to get a more accurate answer if you ask more people. You mathematically can note that because if this number on the bottom gets larger, the fraction becomes a smaller number and it's less error. The second thing to note about margin of error is this, is that the increase in the level of confidence increases your confidence interval. This is your level of confidence right here, Z. So they're saying if you increase your level of confidence, if you go from 90% confident to 95% confident, what it's going to do is make your Z a bigger number. If Z is a bigger number, your margin of error will go up. But if your margin of error goes up, if this number increases, then the confidence interval is going to be a longer interval. Okay? If this is a big number, your interval is going to be wider. If this is a small number, your interval is going to be shorter. So understand how those changes to either the Z, or which is your confidence, or the N, which is your sample size, will impact the confidence interval itself or the margin of error. This very last slide, just to make some good conclusions. You have to keep in mind we are making inferences about data, so you must be cautious. This is not guaranteed information. That's why it's in a probability section. Okay. Things to keep in mind when using confidence intervals. Data collected must be from a random sample. If it's not random, you could really skew your results. Second thing, if a sample size is small, outliers will have a huge impact on the confidence intervals. We learned in Chapter 1 that outliers impact the mean by far more than the median. So because confidence intervals use the mean, they are subject to being skewed quite a bit if there's outliers in the data. Number 3, use confidence intervals requires you to know the standard deviation of the population, which in most surveys is unrealistic. Confidence intervals do have a flaw. They are using what's called the mu and the sigma. Those are calculations of the population, which are assumptions made in statistics. They're not necessarily factual. They're assumptions, so there is some room for error. And then number 4, the margin of error in a confidence interval only covers random sampling errors. If there's something like there was an error in the survey itself, it's not going to cover that type of error. So just keep that particular component in mind. In terms of the homework, what you can go ahead and do is everyone can skip 8 and 9. For modified, though, because you're skipping 8 and 9, you really want to do number 3. Otherwise, you're just not going to know enough for this section. Again, modified folks, make sure you think you're comfortable with doing enough examples to understand the material.